Hello, my name is Michal Mrozek, I'm from Intel, and today, with Ben Ashbaugh and James Brodman, we are proud to present Taking Memory Management to the Next Level, Unified Shared Memory in Action. Okay, here are notices and disclaimers. Read those carefully because this stuff is super important. And here is an agenda for today. First, we'll start with a look of shared virtual memory and how it serves our needs. Then we'll introduce unified shared memory concepts. We will follow with how unified memory plays with our deeply C++ solution. And we will conclude with future plans and calls to action. Okay, so let's look at OpenCL key feature, shared virtual memory, SVM. And I would like to say that we want to focus here on how SVM plays with discrete devices that has local memory built in chip. Local memory is a very fast memory that can be accessed from compute units in a very fast fashion and offers very good bandwidth. GPUs can also access system memory, but this requires to go via PCI, which doesn't have a lot of bandwidth, and therefore it's slower. And SVM actually requires us to have a concept of sharing the virtual memory. So it creates a notion that some kind of a memory is shared. First way to implement a shared virtual memory is to actually create a block of memory in system memory and access it directly from CPU and from GPU over the PCI. The obvious benefit is that GPU accesses the system memory directly. There are no migration, there are no copies, but the problem is that there is low bandwidth due to PCI access, and this path is actually slow. Another way to implement SVM is to actually do the migration of memory. So CPU still accesses the system memory, but whenever GPU is expected to access the memory, we transfer the memory from system to local memory over the PCI, and further GPU accesses the copy in local memory. So it has a good bandwidth, it has a good performance, but anytime we actually need to read the data back on the CPU, we need to do the migration in the other way, which obviously costs performance. So yeah, we need, anytime that the different device needs to access, we need to redo the transfer. Okay, so let's see how APIs help us to achieve what we need. If we look at SVM alloc, it has a context parameter, a flags, the size and alignment. But the obvious thing missing here is where to actually place the memory. Should it be in local memory of the device or in host memory? If we place it on the host, we may run into a situation where actually host never access the memory because a user wanted to allocate a device buffer that would never be accessed from the CPU. So placing it on the host memory would be very wasteful. From the other hand, if we place it on device, the host may actually want it to have a host-based allocation and not do any migration and access the memory over the PCI. So these are like contradicting requirements that doesn't play well, and API doesn't tell us a lot about what the user really wants. If we go further to scenarios where there are multiple devices, where each GPU has its own set of local memory, and the OpenCL context combines multiple GPU devices, the thing starts to be even more complicated. There are even more questions and like where to put the memory. Should we do this on the first local memory that's being used on any device, or should we place it on all devices? Or actually, should we do it simpler, place it in the system memory and all devices will utilize the system memory storage? Should we automatically migrate? If so, at what point of time? Should it happen on events or on access basis or some kind of other heuristics? And how to actively synchronize the contents of the memory if there are multiple devices. And the fastest way to access the memory is actually local memory. And each GPU cannot access others' GPU local memory. So it doesn't play pretty well with the shared virtual memory concept. And driver heuristics are It will help in some kind of scenarios, but will also make other scenarios worse. And that's why they are pretty bad and should be avoided. If we look closely about what are the types of SVM and what they offer, there are many nice capabilities that's really useful, like the pointer representation of SVM allocations. This is really good stuff and makes integrating existing code bases to OpenCL much easier, because existing code bases are using pointers, and SVM uses pointers as well. If we can use pointers across our stack, we can integrate much more easier. What's also nice for fine-grained allocations is that there are no map and unmap calls. It's pretty cumbersome in some kind of situations that in order to access the memory on the host, you actually need to map the memory on the host, and to transfer the memory back to the device, you need to call an unmap. When it's automatic, then it's much easier to integrate it in your code base, because you don't need to care about where the memory is and how to access it properly. Another problem with SVM allocations is that for those types of allocations, we need to specify all allocations that will be used by a given kernel. The SVM resources may be used indirectly, like if you do a linked list of SVM pointers and you hide some pointers from the driver and not pass it on a kernel argument list, then you need to specify those allocations using cl set kernel exec info and passing the list of pointers, which also requires some kind of heavy lifting and tracking this in your applications. And sadly, most of the implementations actually only implement the coarse grain support, where there are a lot of things required from the application's perspective to happen, like you need to do map and unmaps, you don't have like concurrent access, and this way you don't have those benefits of other memory types. So yeah, we thought about it. We've tried to utilize what's currently available in SVM for our discrete solution. And unfortunately, the only way we found to succeed and have a good performance and convenience is to redo and maybe introduce something new. That's why we started the Unified Shared Memory USM concept. And I will now explain what we created and how it works. This is all working. We have it implemented in our drivers in our DPC++ solution. There are multiple applications already using this. We have checked how it works, and we think that this is a way to move forward with how memory is handled in OpenCL. Okay, so we introduced 3 new memory types to give user an opportunity to express what he really wants out of the driver and out of allocations. We have a system memory and GPUs with local memory. So the first allocation type that we introduce is device allocation. Device allocations are placed in GPU's local memory, and their expectation is, oh yeah, I want this allocation to be in device memory, nowhere else. Another type is host allocation, which are put directly in system memory, and they need to stay here, don't move anywhere else. So this is a clear distinction between host and device allocation. Third type that we introduce is shared allocations. Shared allocations can be placed in multiple memory regions, in system memory and in local memory, and they automatically migrate. Okay, I will now go into details about how those allocations works and how the API looks like. Let's start with device allocation. And the main reason to use device allocation is to have the top-notch performance. Those device allocations reside in device local memory. They will never be accessed on the host. They will never migrate. They are only available to this one and only one device. There are no map and unmap calls whatsoever. So this gives driver a clear information that this allocation may be heavily optimized only for device access. There is no need to allocate any staging resources for it. There is no need to allocate any CPU accessible storage. This will never be accessed on the host. That gives driver a lot of opportunities to optimize and place the memory directly in place on the allocation call. We strongly feel that allocating memory is the point in time where the allocation should happen. We want to move this out of the enqueue path, which is a hot path. We want this to happen as early as possible. So device mem alloc accepts context and device. This device is used to specify on which device this device allocation will be used. And this way, a user can easily obtain a pointer, device pointer to the allocation, and use it across its application. Okay. Going further, we have host allocations. Host allocations utilize that GPU may directly access the host memory residing in system memory. So host allocations are available for host and for device. They are available for the host because they are allocated out of system memory and CPUs has direct access to the system memory without any problems. They also do not migrate to the device memory. They will always stay in system memory. Therefore, there are no map and unmap calls because the placement, there are no need for staging increases to move those allocations and so on and so forth. And there are certain situations in which such kind of buffers are very useful, like your host allocations or your staging buffers on the host, or pinned memory, which you can use to do various transfer calls. There is no device placement in the API because those kind of allocations are available for all devices that reside in the context. You can also oversubscribe this memory because usually the systems will have the more system memory than device memory, so you can allocate much more memory than the device has. It's also represented as pointer, and there is an address equivalence. So address returned by this allocation will match the address that the GPU will see. So you may propagate linked lists and all the SVM tricks that are available with the pointer arithmetics. Okay, so these are host allocations. This is how they are used. CPUs access the host allocations directly because they are in system memory, and GPUs access this memory over the PCI. Okay, going further, we have shared allocations, which trades the control of the placement for the programmer convenience. So shared allocations automatically migrate. They have shared host to device ownership. We can specify an initial placement for shared allocation, but they are also available in all devices that the context contains. They automatically migrate on a per user basis. So whenever CPU access, the allocation will automatically migrate to the CPU, and whenever the GPU access, it will automatically migrate to the GPU. And they are also represented by the pointer, and there is an address equivalence. So let's look how they migrate and how this works. We have a CPU and GPU, and we allocated such allocation. No one used to touch the allocations yet. Let's say that CPU wants to access this allocation, so driver will ensure that the allocation is in system memory and CPU can access it. So CPU will utilize this allocation and propagate the contents. When CPU is done and the GPU starts to use the allocation, this will give a signal to the driver that, oh yeah, now GPU wants to use this allocation and we need to move it to the GPU domain. So we will move the allocation over the PCI. This is the automatic migration. The allocation will actually move to the local memory from system memory. So GPU can access this memory efficiently in the local memory. GPU will now utilize this allocation and the contents will be here. And going further, if we want to look now how CPU can access this allocation, which now resides in the GPU local memory, so CPU will try to access, like you do a pointer dereference and you start to read from the pointer of short allocation on the CPU. That will give a signal to the driver to automatically migrate your memory out of the GPU to the CPU, and then CPU can read the contents from the system memory. So CPU doesn't read the allocation over the PCI to the local memory, it reads it directly in system memory. Okay. Here I'll explain the calls that we added to actually free the memory. We have two calls. We initially started with the CLMem free intel call, which just freed the memory in place. But we discovered that for convenience, some users do not want to track if the pointer is still in use or not, and CLMem free intel actually requires you to do so. You need to make sure that the pointer is not used by any device, because you may free the memory in place. So we introduced a second version of the free call. We call it CLMem blocking free intel. This call ensures that all operations are completed and the pointer may be freed. And this gives very nice convenience to the application, because it doesn't need to track all the usages, all the submissions, and all the stuff. It can just call CLMem blocking free intel, and this call will ensure that all the operations are completed and memory is freed properly after synchronization. Going further, we've also added improved the concept of indirect access. So if you want to do indirect access in OpenCL, you need to call CLSetKernel exec info with CLCat info SVM pointers, where you pass a list of pointers. What we discovered, and I've seen like multiple cases like that from our clients, is that when they start using SVM, they tend up to have huge numbers of allocations. Like the applications that I saw was using 10,000 pointers, and due to indirect access, those applications were passing all those 10,000 pointers to this CLSetKernel exec info call. And that takes a lot of time in the driver to actually validate, because driver needs to take this list and it needs to check if all those pointers are actually valid. And those pointers may be offset from the base, maybe out of range. So this is not like a simple comparison operation. We need to check ranges if the pointers that are passed fill into those ranges. So this call for 10,000 pointers is actually taking a lot of CPU clocks. So what we wanted to fix here, we added a notion of indirect access flags. So we have 3 memory types, and each kernel can be set to specify that those kind of allocation types are used indirectly in this kernel. And user may simply say, oh yeah, in this kernel I'm using this allocation type indirectly. Make sure I can use all allocations that were allocated in this context indirectly. So instead of passing like 10,000 device pointers or host pointers to the kernel, user may just say, oh yeah, in this kernel I use shared allocations indirectly. And that's it. That's it. There is no need for application to pass 10,000 pointers. There is no need to track all the partials. And also, driver doesn't need to validate anything, because driver contains the list of shared allocations, and it can simply allow them to be accessed indirectly in the kernel. So this call fixed this performance problem and saved a lot of CPU clocks for our clients. They simply removed all the tracking logic, all the pointer combining and creating this big array of pointers, and they simply, oh yeah, I'm using this type of memory indirectly, make sure that I can use it. Okay, going further. We also added some calls for convenience to retrieve information from the pointers using the driver. So when you start going with pointers everywhere, you may lose track about what's the base pointer of my allocations, what's the allocation size, or what's the type of my allocation. CLMem objects like buffers has dedicated calls to retrieve those kind of informations. We added similar calls for pointers as well. We call them CLGetMem alloc_info_intel, where you pass a pointer and you can obtain all those information like allocation type, base pointer, allocation size, or associated device, or the flags that were used for creation of such resource. So user don't need to track this on its own. it can ask the driver at any point of time to retrieve those informations, and driver simply knows all the allocations that it did in the past and know all the metadata associated with it, so it can retrieve this information to the user very easily. Okay, so how does unified memory play with our DPC++ solution? And a word of introduction: DPC++ is actually Intel approach to have SYCL plus C++ plus Intel extensions available as a standard. So DPC++ is a standard that contains all those 3 key pieces, and we strongly feel that unified shared memory is a huge step forward in making sure that applications can be integrated super easy to existing code bases with basically a minimal effort. So unified shared memory, addition to SYCL, simplifies a lot of things, and I will show them in a second. It allows for easy integration, and it adds greater control of memory ownership and placement for users that actually care about this. So let's do a unified shared memory code walkthrough from SYCL perspective. We've introduced new functions to allocate memory. They are templated malloc calls. Like here you see a malloc shed that basically allocates a shared memory of a given size in a given device and in a given context, and returns a pointer that application may simply use. So this pointer can be used right away and are associated with a device that's available in the SYCL. These allocations may also be used right away when we speak about host and shared allocations. For device allocations, we need to do manual transfers because they are not available on the host, so there are copy APIs. And as you see here, we directly initialize the memory right after the allocations. So there are no like mapping or any kind of accesses. The memory is available right away. You may use it. And also, what's very crucial, when we pass memory to our Lambda, the encapsulation happens automatically. So the pointers, the unified memory pointers that we allocated in our SYCL code can be used right away. There is no need like for accesses and so stuff like that. We also added some new mechanism to control dependencies between the queue operations. We've added depends on, where we specify like another lambda that's used to express dependencies. We also added in all the queues to SYCL, which enhance the default, which is out of all the queues in SYCL, to have in all the queue capabilities to actually mimic the OpenCL behavior. And so here we use the shared memory on the device, this generated device code, and we will wait for completion of this operation. So as you see here, the lambda is super simple. The memory is used right away. There are no accesses code. And when the operation is actually completed, we can use the memory right away on the host as well, without any accesses. So the shared memory is already available. We do a memcompare here for the contents of the buffer. And then at the end, we clean the buffer. So if we want to see at the complete example, this is it. This is actually the complete code with actually a quite big font and comments and spaces in between that's doing everything. And we think that's purely awesome. If we can fit the whole code that does the GPU computation, memory allocation, memory comparison, and resource cleanup. As you see here, resources can be used without any additional stuff, and both on host and on device. And there is no need for expressing the migrations, so users with such convenience can integrate to their existing applications very easy. Like these guys are the pointers, so they may be passed to other layers that using pointers on the host without any modifications and any kind of actual additional tracking. So we think that's pretty awesome, and that will help to actually create very simple applications that can be easily used, easily explained, and therefore it would help improving the ecosystem. We have few versions of this malloc. There's malloc device, malloc host. Here we show the malloc shard. The code would be exactly the same with malloc host. With malloc device, we would need to transfer the memory. But this is for the users that wants much more control about placement and don't care about super fast prototyping. Okay, so yeah, what are the future plans and call to actions? We actually recommend to start using the unified shared memory, and we will try to include this in future standard both for OpenCL and SYCL. We strongly feel that they improve standard a lot. They give drivers insane amount of possibilities to optimize. They give drivers a lot of informations about how to properly place the memory, what's the expectations from the user, and we strongly feel that those kind of improvements are really needed if we want to have efficient implementations on discrete devices. We will also continue to develop unified shared memory in DPC++, enhance it, add new things, add new features. We have not explained everything here because there are much more calls. If you're interested, we have docs with extensions explained deeply with all the API calls. This is just like a top of an iceberg. We also encourage you to try unified shared memory. Your feedback is very valuable to us. We want to know if this all makes sense, if it's easy to use, if you get the top performance out of it, if you find it convenient, useful. Please try it. And if you find the USM useful, encourage other implementations to support USM as well. So with that said, here is my thank you. Thank you for the opportunity to present at IWOCL. Here are useful links that you may use. Here are samples. And having that said, have a good day.